Continuing on with Unit 2 Test Study Guide, we are on question number 20, converting between interval and inequality notation. There is this question, all real numbers except 5 in interval notation. This is the correct way we write that, with interval notation, where we basically exclude the value of 5. So we go 5 union 5, and then we use everything else, so from negative infinity to positive infinity. Converting between the notations, negative infinity to 5, negative 2 less than x less than or equal to 12, 3 less than or equal to x less than infinity. Here are our answers for this translation. The key idea coming that open dots from when we graph them represented less than and greater than, which means in interval notation we use a soft bracket, which is in fact a parenthesis. With solid dots that we graphed, we use less than or equal to, greater than or equal to, which means that we use a hard bracket when I'm using and translating between those. Also remembering that we always use soft brackets when I use positive and negative infinity. Next page, determine what the domain and range of a function. When we're reading a graph, we always read it from left to right, the way that we normally read left to right. That helps us when we talk about domain and range, also increasing, decreasing, constant, positive and negative, and how we answer, as we'll see later. So, looking at our graph, these graphs look familiar. They're from earlier. We're looking for the domain of this graph. Once again, when we're looking at domain, we're looking where the graph starts to where the graph ends, and we're looking for any vertical asymptotes, any holes, or any gaps that occur as I move from left to right on my function. We're looking for gaps that occur in the left and right of our function, and we're going to list them. For range, we're going from down to up, so we're going from the lowest point to the highest point. We're looking at where it starts to where it ends, and once again, we're looking for horizontal asymptotes, dotted lines that we're not crossing through, any holes that may occur, and we're trying to exclude those. So looking at our graph, look how far left this graph goes. We see that there's an arrow, which means it goes forever towards negative infinity, and we see this arrow going up and also over, which means it goes to positive infinity, which means the domain is going to be negative infinity to positive infinity in interval and inequality notation. Now, for the range, let's start with how far down the graph goes, and we see that the lowest point in terms of y values is negative 4.5, and the highest the graph goes, we see that there we have arrows, which means it goes up to positive infinity. And there are no breaks in between in terms of y value, just like there were no breaks in terms of the x values, no vertical asymptotes, no holes, giving us a range of negative 4.5, comma, infinity, with a bracket and a parenthesis to match our negative 4.5 less than or equal to y less than positive infinity. Next graph. Looking left to right, how far left does this graph go? We see that it actually only goes as far as x's value of equal to 2, but it does go to the right forever, which signifies positive infinity, giving us 2 to infinity, both interval and inequality. Notice again, we never actually touch this value of 2, so that's why we're using the soft bracket. And since there is no other portion of the graph on this side, I'm not going to go to negative infinity because there is nothing on this side. The graph is not there, so I can't talk about values that don't exist. For the range, how far down does this graph go? Well, this arrow is going over and down forever, so that goes to negative infinity. And this arrow signifies it goes up to positive infinity, giving us a range of negative infinity to positive infinity. Question number 27. Looking at the domain of our graph, it looks like the graph goes down and over to the left forever, so that's negative infinity. There's an arrow going up, which means it's going up to positive infinity and out to positive infinity. And there are no vertical asymptotes or holes or anything, so our domain is negative infinity to positive infinity, and the range is also negative infinity to positive infinity. Now, these graphs were relatively easy. I would like to point your attention to this domain and range document we did in class. It has 9 graphs on it. This is a pretty good indication of the level of difficulty from easy to hard to challenging that you're going to experience on the test and also throughout the year in terms of domains and ranges. This is a great other study tool for you to take a look at. You can also look at the classwork that I gave you, which had another 8 graphs, and also a review of the key points to go along with the notes practice that you did, and one example down there. Also the notes practice on page 5. So lots of great domain and range practice activities for you. doesn't just have to be the domain and range problems number 25 through 27 on the study guide. Okay, moving on to increasing, decreasing, and constant. Question number 28, we're always looking at the x values. This is how we answer our question. We must look at the intervals of x where the y values are increasing or decreasing. So we always answer in terms of our x values, even though we are looking at the y values, whether they're going up or down. Question number 29 through 32 are asking us to identify the different intervals that are listed there then. So in number 29, we see we are increasing. The graph is going up in this portion, and that is starting at x is equal to 4 all the way to positive infinity. We see the graph is going down in this portion of the graph as I look, as always, left to right across the graph. So that's negative infinity to 4, and there is no place where the graph is flat. Question number 30, looking across the graph, we see that this graph is not increasing anywhere. It is not being constant anymore. It's actually decreasing everywhere we see a graph, and that is everywhere, but it actually starts at the x value of 2. So from 2 to infinity, this function is decreasing. It's not being flat anywhere, not going up. Always, as I look from left to right, the graph is just always going down, and the graph exists on the right-hand side of 2 all the way to positive infinity. Question number 31, where is this graph going up? Where is it going down? Where is it flat? You see the graph is going up in these two portions as we look from left to right. What x values is that? Well, that means from negative infinity all the way to 1/2, and then 5 to positive infinity, our graph is increasing, meaning that the graph is going down in this region. That is from 1/2 to 5. And this graph is never flat, so it is never constant. Question number 32, where is this graph increasing, decreasing, constant? This graph is increasing from negative infinity all the way up to an x value of negative 4. And once again, it starts at 0 increasing and all the way to x is equal to positive infinity. It is never going down, but it is flat in this middle region, and that is between x values of negative 4 and 0. Once again, we're answering just in terms of x values on these types of questions. We're looking at the y values, but our answers are purely in terms of the x. Okay, question number 33. Continuous graph has no breaks in it. Continuous means that there are no breaks. A discontinuity means that there are breaks in the graph. And what types of discontinuities do we know? Well, we had 3 types of discontinuities. We called those point or removable, jump, and infinite or asymptote discontinuities. Remember, points were like potholes. The graph appeared on either side immediately. Jumps are like teleports. The graph has to move to a new location. And asymptotes we can clearly see with vertical asymptotes. This comes from page number 3 in our notes from topic 2, characteristics of graphs. So back to our review. We clearly see that there is some type of discontinuity at x is equal to 1 and some type of discontinuity at x is equal to 2 in these two graphs. But the type we're looking for here, we see that this is in fact a jump discontinuity and this is an infinite discontinuity. It's infinite because we can see that there is a vertical asymptote. On this, we see that the graph is moving, comes down, and then all of a sudden it has to start up in a new location on the other side. It doesn't exactly show up on the exact opposite side of this hole in our graph, so we would call this a jump discontinuity. Make sure you know how to tell the difference for the test. Okay, end behavior function. This is what's happening as the graph goes to the left and as the graph goes to the right in terms of our x values. We're looking at what the y value is doing. So as x approaches positive infinity, then f of x approaches negative infinity refers to which side of the graph? Well, positive infinity means we are going to the right-hand side. So, right. As x approaches positive infinity, then f of x approaches positive infinity. Which way is the right side going? Well, this is my right side. Positive infinity means to the right. Well, the graph is going towards positive infinity. Well, f of x just means y. So that means the y values are going to positive infinity, which means up. Take note of this. This is a great way to ask it without actually giving you a graph. Questions number 38 and 39 are what happens when I give you a graph. As x approaches negative infinity, that means what's happening as I go this way. Well, we clearly see the graph is going down, which means it's going to negative infinity. As x approaches positive infinity, that means as this side of the graph, we see the graph is going up, which means to positive infinity. Same thing for 39. What's happening as I go towards negative infinity? Well, we see the graph is going down, which means negative infinity. And as x approaches positive infinity, what's going on to the graph? It's also going down, which is positive infinity. Now remember, it could be negative infinity, it could be positive infinity. It could also trend to some number. We talked about it could just get flat on our notes. We could see it either if there's a horizontal asymptote, sometimes it just the graph trends to that number. Sometimes the graph does not, there is no graph over there, so we have to say does not exist. This is very, very rare, but usually our three options are going to be going down to negative infinity, up to positive infinity, or horizontally getting flat towards some type of number like we've shown in the note. Okay, question number 40 is basically putting together everything we've done up to this point on one particular graph and labeling everything we know. So this is really the whole unit all in one problem. So here are the answers to this big mega problem. If you're struggling on each of the individual sections, go back and take a look at the video notes. Go back in each of the little sections of this review, but hopefully you're looking at these answers and you're getting them right. I'll zoom in very slowly for you. Here is the top portion. And here is the bottom portion, domain and behavior. There is the complete solutions and comes to the end of our review.